I'm Rich Wagner. It's the third or fourth or fifth Chesapeake Forum talk I've given over the last, back when it was called the Academy for Lifelong Learning. This is the one probably closest to what I actually have some experience in myself. 60 years ago, last April, Janae and I went to the town of Livermore, California, which was a cowboy town at the time. They also made some wine. I was a brand new Ph.D. Went to work in a group that was working on Livermore as one of the two national nuclear weapon labs. Nuclear weapons are very complicated, and you need giant computer code using them at every instant over the last 60 years, the largest computers in the world, and some of the largest computer programs, codes, to calculate the performance of weapons. And since it's very hard to do experiments, to make measurements on nuclear explosions, you have to look where you can to validate the codes. And so you look at stars. And my first assignment in the group that I went to work in was to write the equation of state, the relation between the pressure, the volume, the temperature, and the amount of material. The equation of state for a collapsing neutron star. Neutron stars were not known to exist at the time, but it was thought that they might. And my boss, Jim Wilson, was going to try to calculate the implosion and then the stable existence of a neutron star in order to help validate the weapon design codes. Jim was a world-class physicist, a world-class mountaineer, and a world-class free spirit. He was really a remarkable guy. He went on to spend most of his career establishing the field of what is now called computational astrophysics, which actually did end up predicting the existence of neutron stars back in the 60s. And then in the late 60s, somebody observed a thing that turned out to be a neutron star. I did a terrible job of writing the equation of state, but it was the best that existed at the time. And Jim used it in his codes. This is going to be a PowerPoint talk. My métier for the last 55 years has been PowerPoint. It's going to consist of both words and pictures. I have studied a little bit how you convey information in talks, and if you use both pictures and words, you cover everybody. And if they're together, it's better than if they're separately. So I'll talk through a lot of PowerPoint slides. If you have questions, again, speak up, and I'll if I don't repeat your question, remind me to repeat your question. So, Jenny, you want to advance the slide? This is about the behavior of matter at extremely high temperatures, like millions of degrees or hundreds of millions of degrees, and pressures that approach the pressures at the center of the sun, and densities that are very, very high. Now, these conditions exist in three places in the universe: in stars, in nuclear weapons, and in experimental machines that attempt to produce nuclear fusion here on Earth. Nuclear weapons do that, but it's not controlled, or not controlled to generate power. The national labs at Livermore and at Los Alamos, which was the center of the Manhattan Project, are the only places that really work on all three. Livermore, starting about 30 years ago, built what came to be called the National Ignition Facility. It's where a successful laser-driven nuclear fusion experiment was done. Success meaning that the fusion energy created was a little bit greater than the laser energy that compressed the nuclear fuel. I'll talk about all that considerably more. Next slide. I want to give you a little bit of background on some physics and chemistry. So I'll talk about atoms and molecules and the atomic nucleus. Next slide. So here's an atom with a little tiny nucleus, and around it some electrons. In the Niels Bohr model, they're sort of like little planets orbiting a sun, which is the nucleus. They're not really. They're sort of, their reality is mainly mathematics. But it is the electromagnetic forces that exist in the electrically charged electrons and the electrically charged nucleus. The electromagnetic forces that operate to power chemical reactions. Down here at the bottom, the diameter of an atom is about 100 millionth of an inch, and the nucleus is, if you can think in terms of a diameter, about 10,000 times smaller. So this is tiny, tiny stuff that's going on. Next slide. So here's an example of chemical energy. This is a sugar molecule. The spheres are atoms. The links between them are the electromagnetic forces that hold them together. Those forces, as forces go in the universe, are relatively weak. So you don't get a lot of energy from chemical reactions like burning sugar in your body to metabolize it, but enough to make most reactions in the world work. Next slide, please. Now, turning to nuclear energy, there are two ways of getting usable energy from nuclear reactions. I guess actually any energy from nuclear reactions. Nuclear fission. Today, fission generates about 10% of the world's electricity. Maybe it's 8%, maybe it's 12%. The US generates about 20%. France generates about 70% of their energy with nuclear reactors. And China is growing in that regard. India generates quite a bit. And fusion. I should say that the thing that's wrong with nuclear fission is that it generates radioactive waste that has to be handled carefully. Not a whole lot of it, but you've got to handle it very carefully for decades or centuries or millennia. Nuclear fusion is what powers the sun. The fusion reaction, which I'll talk about on the next slide, is a little bit different from the reactions that one hopes to harness in nuclear fission on Earth. It's not yet developed for terrestrial use, but if it could be developed, it would be clean. Maybe 1% of the long-lived radioactive materials that fission has. And the fuel is plentiful. And an important thing, I think, these days is that it would use the existing electric power infrastructure, so you don't have to build new infrastructure. It would operate in centralized plants like coal, gas, and so forth. Next slide. So this is nuclear fission. This is a uranium atom, uranium nucleus. Another uranium nucleus in a metal oxide, of which the metal is uranium. This little blue blob at the top, green blob, I guess, maybe coming in, is a neutron. Coming out of the bottom are 5 neutrons, and maybe another one there that goes, I'm not sure where this slide had it go. The blue blobs are sort of half or a third of the original uranium nucleus, and they are what is radioactive and has to be handled as waste. The yellow star is the energy created, and it creates more than the one neutron that comes in. So you can get a chain reaction, one neutron leading after several fissions to 5 or 6 or 8, and that can go on. Controlling that reaction so that one neutron only leads to one more fusion is what happens in a nuclear reactor. In a nuclear weapon, it's basically uncontrolled, and so the chain goes on and multiplies a lot. Next slide. So this is nuclear fusion in contrast to the previous slide on nuclear fission. Nuclear fusion uses the binding energy of the nucleus in order to create output energy. This is, deuterium is a heavy form of hydrogen. Normal hydrogen has a single, let's call it a proton, which has an electric charge, a positive electric charge. Deuterium has an additional neutron bound with what's known as the strong force, not a very imaginative term, the strong nuclear force together to form a deuterium nucleus. You can add another neutron to the hydrogen proton and make tritium. That's the main fuel in terrestrial nuclear fusion. It's the reactions between two normal hydrogen atoms are what occur in the sun, but I'm not going to talk much about what goes on in the sun. The fusion reaction results in two products, one neutron and one helium atom. Helium because it combines the two neutrons, the two protons, the two hydrogen atoms into a single nucleus, which is the helium nucleus. Plus energy. 1,000,000 electron volts is a convenient unit of energy for this kind of energy. So the neutron that leads the fusion reaction carries away 14 million electron volts, and the helium nucleus carries away 3.5 million electron volts. The neutron leaves the fusion system. It will penetrate, a neutron of that speed will penetrate feet of lead, for instance. But the helium nucleus, because it has electric charges on its two protons, slows down very rapidly. And that can, if you manage things right, can further heat the fuel and produce more fusion reactions. The way that the fusion works, the reason the fusion requires very high temperatures is because these two nuclei repel each other electromagnetically because they're charged, and they're both positively charged, and like electric charges repel each other. So you have to overcome the repelling force between the two protons by raising this material to a very high temperature, like 100 million degrees. If it's going that fast, the two nuclei are going so fast that they can overcome the repelling force, the electromagnetic force, and get down to distances from each other where the very short range, but much, much strong nuclear force takes over, pulls them together, and causes them to fuse. Einstein had forgotten how to make a superscript on PowerPoint, so it's mc squared, but that's how this comes about, and the same thing is true in the fission reaction. I think I've said everything I want to say about that slide. Thanks. So there are two main approaches to developing fusion power. I'll use the word burn a lot. I don't mean chemical burning, I mean nuclear burning, fusion burning. So to burn, the fusion fuel must be heated to very high temperatures, compressed to very high densities, and then confined for long enough that the reactions can go some distance toward completion. You can confine it in two ways. One, using very strong magnetic fields to confine the burning fusion fuel. The objective is to confine it for very long times using very strong magnetic fields produced by very large electric currents. One of the other fundamental things in physics is when a charged particle crosses through a magnetic field, it is turned in its flight. And if the magnetic field is strong enough, the electrons and the charged nuclei are sort of wrapped around themselves, just like happens in northern lights, and but much tighter wrappings up, and won't leave the system. They will be in a sense refracted back into the system, so that the fusion reaction can continue. The other approach, which is going to be the main focus of what I'll talk about today, is called inertial confinement. You use the mass of the system itself rather than a magnetic field to produce a very short but a powerful confinement time, about trillionths of a second in the experiments that I'll talk about. And eventually, if you can repeat that over and over and over and over again for months or years, you've got a fusion reactor. This goes on in a small capsule that I'll talk a lot about. The capsule wall is the mass that confines the fusion fuel for long enough so that it can burn, hopefully, to near completion. The sun's fusion energy comes from the inertial confinement of the mass by the giant gravitational force of the mass in the sun. Next slide. So here's a simple slide of a star. 3 layers or 4 in a star. Down in the very center, so this could be the sun, this is the surface of the sun here that we see. Down about 1/5 of the radius is the gravitational compression heats the fuel to a high enough temperature so that fusion reactions will occur. That energy from the fusion reaction, which is mainly particles of light in a thing as large as a star, that energy is carried outward. Oh, there it goes. That energy is carried outward through a radiation zone, radiation region. I think I'm about out of electrons here. Through a radiation region, and then it becomes a convective region, just like the boiling water in a kettle on your stove. Carries energy to the surface. By the time it gets to the surface, which is has much more surface area than the small fusion region down in the center. By the time it gets to the surface, it's 5 or 10 or 20,000 degrees, and that's the surface that you see. It's the coronosphere is what happens in the sun when all of these electric currents from the reactions get to the surface and begin to interact and form loops of magnetic field and loops of electrons generally, but also protons, following the field and going through very, very complicated gyrations in the coronosphere. You don't see those except in eclipses, but they're there all the time, and they're what cause sunspots, the solar wind, particles impinging on the Earth's magnetic field to create northern lights. Next slide. To try to do that in a terrestrial system requires a giant machine. I don't think my laser is working. Can you all see that?
Yes.
Yes. Now you can't do it. Something wrong here. Okay. Sorry about this. Here. This donut that goes around that center pillar is about 15 or 20 feet across, 20 or 30 feet in diameter and 10 or 15 feet vertically, and wrapped around that donut are electric conductors, these days superconducting wires that create the magnetic field that surround the donut, inside which is the burning fusion fuel. All this stuff out here is apparatus that supports it, but this is a diagram of an experiment that's going to be conducted in 7 or 8 years at some place in Europe, I've forgotten where, which is the sort of the culmination of an international collaboration to produce fusion fuel this way. I think so. The difficulty of confining the fuel until it can burn in this donut is what governs the duration at which the burn can occur. Next slide, I think. Well, all right. So this is a closer up picture of the sun's coronosphere. It illustrates the complexity of the confinement in a magnetic fusion reactor. Astrophysicists and people who study that kind of physics have tried to model with giant computer codes the behaviors of the electromagnetic fields in the corona of the sun and have failed abjectly so far. And it is a giant triumph of that kind of physics that, next slide, please, in a predecessor to the ITER machine about 7 or 8 years ago, they confined the burning fuel for 20 seconds. The objective, of course, is 10,000 times that, a number of years, a million times that, for a year or two. So they've got a long ways to go. In another 10 years, ITER might work to produce continuous, or at least many weeks or months of fusion burn, which then would make it a sort of a pilot plant. And perhaps another 10 years beyond that to a commercial power level electricity generating plant. So that's sort of the future of magnetic fusion fuel, magnetic fusion. The next slide, I'm going to turn to my main topic today, and that is the December 2022, 7 months ago, inertial confinement laser fusion experiment at Livermore. Next slide. A laser is an acronym for light amplification using stimulated emission of radiation. This is a tiny bench, well, not a tiny laser, because this is a tiny laser and there are much smaller ones, but a sort of a bench level size laser. And the way it works is you pump energy into a gas in that kind of pinkish cylinder in the center, and the first light that goes through it stimulates the emission of the energy stored in the electrons around the nucleus of the gas in the pink cylinder. And if the light reflects back and forth every time it goes through it, it extracts more energy at exactly that same color, and eventually coming out the exit down here, it is quite intense. So the next slide shows the ignition facility at Livermore. Here's a car down here parked at the outside, so that gives you the scale. It's about the size of 2 football fields set side to side. All of the well, I got to replace the batteries. All of the sort of yellow and pink things there in the center are lasers. There are 192 beams of lasers, each one much more powerful than the little one that I showed in the previous slide. They are all brought down to the center and focus from mirrors.
Rich,
Not
why
working.
don't you just take a pen and go up and stand by the thing?
No, I could go stand over there. Is anybody having trouble following how I described this? Okay. Now I'll walk over if I can do it. This apparatus right there is a target chamber with 192 laser beams being reflected and focused into it. And the target chamber is about 20 feet in diameter, made of strong steel, with a tiny cylinder in the upper right-hand corner that somebody's holding with tweezers, inside of which is a much tinier target capsule, which is about 0.5 millimeter in size. And in the center of the chamber, in the upper right-hand corner, is the target capsule. I'll amplify on this in the next slide. And this is one of the two slides that you have in your handout. I printed it so because the print's kind of small there, and I'm going to spend some time on this slide. So in the left-hand cartoon is the tiny pellet in the center of the target chamber and the chamber is called a Hohlraum, German for empty volume, and a term used a lot in this business. And the kind of purplish things coming in from the top and the bottom are the laser beams, 192 of them, focused through a tiny hole and absorbed by the gold wall of the Hohlraum. Gold, or Du, stands for depleted uranium, something with a high atomic number, heavy, and the laser energy basically heats the walls of the Hohlraum, and the hot walls now at a temperature so that they're the light that they emit is in the X-ray region. That light impinges on the outside of the tiny capsule. It'll work again. On the outside of the tiny capsule, evaporates the material on the outside, and because of Newton's second law that for every action there's an equal and opposite reaction, the outward going momentum of the evaporated and raised to very high temperatures, the evaporated wall pushes a shock wave inside, which compresses the gas in the center of the target capsule. The center cartoon shows the target capsule. The design of the target capsule is done the same way you design nuclear weapons, with much the same computer codes, these giant codes in the giant computers. And its configuration and materials have evolved a lot over the last 30 or 40 years that people have been working on this sort of thing. Today, the best choice of the materials is the center thing says HDC, which stands for high density carbon, which means diamond. And I'll talk in a little while about how you fabricate these things, which is a miracle in itself. Inside the diamond is a layer of frozen hydrogen, the deuterium and tritium gas that will fuse, inside of which is deuterium and tritium gas. When that is imploded down to about 1/10 of originally its tiny volume, it raises the temperature to about 100 million pressure to about 100 million atmospheres, and the temperature to about 100 million degrees, a couple of 100 million. And that's hot enough and compressed enough for it to have fusion reactions go on. And that's where the fusion energy comes from. Next slide, let's see what more I can add. This is a sort of another view. I got the slides from a talk that was presented by people at Livermore about a year ago. I'll digress to say that the December 2022 experiment was not the real breakthrough that made the front pages for a while. The real breakthrough came about a year beforehand, in August of 2021, when for the first time, the calculated fusion energy burn agreed with the experimental energy fusion burn. And then they tried it again a few months later, it didn't work at all. So it wasn't just luck. By December 2022, they had the diamond was uniform enough and spherical enough, and the frozen hydrogen around the inside of the diamond was of uniform enough and smooth enough so that, and of a somewhat different design, so that it largely agreed with the calculations, and it worked. It got about twice as much energy in the December 2022 experiment as in the previous experiment. And that was enough to exceed the laser energy that was put into the whole round and make the headlines. The real headline should have come for that first experiment that got them up on a much higher plateau of performance. So let's see, this shows much the same thing that I just talked about. It's got a few more numbers on it of temperatures and densities. 100 times the density of lead, ignites at about 100 million degrees centigrade. The helium atoms depositing their energy from the fusion in the fuel itself heat the fuel up in that experiment to about 600 million degrees centigrade, at which the burn proceeded. Only about, I think, 5 or 10% of the fuel burned before the energy of the burning fuel blew the capsule apart. So the objective in the further future, which I'll talk more about in a minute, is to burn 80 or 90% of the fuel before it blows itself apart, which may require a redesigned capsule and other kinds of redesigns. Next slide. So the maximum fuel inward velocity is about 1 million miles an hour at the boundary between the frozen fuel and the gaseous fuel in the capsule. The maximum fuel density is about 100 times the density of lead, fuel temperature 200 million degrees, and during the burn about 400 million degrees, and that all lasts for about 1/1000 of a second. The folks at the labs have their own vocabulary. The times are all very short, and the unit of time is a shake, like the shape of a lamb's tail. A shake is 10 billionths of a second. That's 10,000 times longer than this one, so they're going to have to come up with another term as an abbreviation for the times, and maybe temperatures too. A less imaginative unit that we talk in terms of is an energy unit, which is actually it's about the energy that came from this experiment. Okay, next slide. I want to talk for a minute about fabricating that tiny capsule. It's a miracle in itself, and it involves a team of hundreds of people around the country and around the world, including, the development was done at Livermore with considerable help from the General Atomics Company in Southern California. But these guys tracked down a jewelry company in Berlin that can actually do this kind of thing over and over again. When I say over and over again, I mean about once a month. So the first thing you do is you make a the word teensy is a highly technical term. You make a mandrel, a form that is you polish it to be extremely smooth and round. I won't go into partly because I don't remember exactly how round the silicon mandrel has to be. The next step is to vapor deposit, and the third bullet, is to vapor deposit a very thin spherical shell of diamond on the outside of the silicon mandrel. Vapor depositing carbon to produce diamond requires temperatures of order 1,000 degrees and densities of the carbon gas at that temperature that are very tightly controlled, so that what you end up with is carbon in the form of diamond as opposed to a much more amorphous, less dense material. So it took a decade to develop the vapor deposition technique to make diamond. Then in the outside of the very thin diamond shell, you drill a teensy-weensy hole in the thin diamond shell. You insert a hollow fill tube, much smaller than a human hair, which is uniformly has a hole through the middle of it. You place that in the tiny fill hole that you have just made, and you weld it in place. Welding is in quotes because it's a complicated process of joining metal materials with carbon. You then through the fill tube, you fill the diamond shell with polishing paste, and for a couple of weeks you go through a complicated sort of like grinding an astronomical telescope's mirror or lens. A very complicated process of introducing and extracting different grades of size of the polishing paste. And you polish the inside of the diamond shell until the irregularities are smaller than a bacterium. Now, how they know that is in itself an immense story of what's called metrology, how you measure things. But the resulting inside of the diamond shell has irregularities smaller than a bacterium. Then you remove through the fill tube the polishing paste. Then you fill the shell with high pressure deuterium and tritium, forms of hydrogen that are the fuel, and you freeze it to about 400 degrees Fahrenheit below zero, at which temperature the hydrogen, deuterium and tritium, freeze, form solid hydrogen. And if you do this all exactly right, you have made a very thin shell of solid hydrogen on the inside of the diamond shell. Inside that, any solid material has some vapor above it. So inside that is hydrogen, deuterium, and tritium in a vapor form, and that is what results in the capsule that I showed in the previous few slides. While it's still frozen, you place it exactly at the focal point of 192 lasers inside the 5/8 of an inch hole round, and proceed to the experiment pretty quickly before the frozen hydrogen melts and evaporates. So that's the process, and I'll just go through these slides again so that you can see the capsule in the center thing there, and then it being imploded on the right. Next slide. So the objective of all of the experiments, of course, is to validate, to use the measurements of the details of the experiment, to validate the calculations in detail so that you can use the calculations to gain confidence in them to to design improved future capsule designs, and to make sure that it's not luck, to make sure that it's what you expected. I'll talk about one sort of measurement, which in itself is a sort of a miracle. This whole thing is a sequence or a nested shell, a nested set of little miracles. Before that, I'll just talk for a second about the second bullet, the neutron pinhole picture. You know, you can make a pinhole picture by taking a piece of paper, holding it up to the sun, make a little pinhole in it, and the paper intercepts the sun rays except those that go through the pinhole. And because they're diverging just a tiny bit because the sun has, you know, that diameter in the sky, it'll form an image of the sun on a piece of paper behind the pinhole. But you can do the same thing with neutrons. But because you can't use paper because the neutrons would go through it as if it weren't there, you have to drill a hole about the size of the burn, a tenth that size, through about 2 feet of lead or depleted uranium, and it's got to be exquisitely straight. And that in itself involves a small miracle. What I want to talk about on the next slide is using what is in effect a phenomenon like, you know, when a fire truck is coming toward you, it's a high frequency. When it's going away from you, it changes to a lower frequency. That's called the Doppler effect. And you can use that to measure the temperature by measuring, by using the neutrons to measure the temperature. And how it works is, so you've got two of the nuclei of deuterium and tritium, and they're coming together to fuse. If they happen to be at a high temperature, some of them will be going in that velocity as they relatively gradually come together and fuse. And because momentum is conserved, the neutron that comes out in the direction they were going is a little higher energy. And if you can measure the energy of that neutron, it's a measure of the temperature of the material of the fusion fuel. The way you measure the energy of that neutron is by measuring its velocity. The way you measure its velocity is when it arrives. So you know when the bang time in the bottom bullet occurred. That's the trillionth of a second during which the burn happened. And you can use that as your reference time. And then the time that the neutron that emerged from the fusion proceeding toward the pinhole, the time that arrives is a measure of the energy of that neutron. The normal energy of the neutron is 14 million electron volts, which was on an earlier slide. At these temperatures, the highest energy neutron, because the fastest neutron, because it was going in the direction of the two fusing nuclei, is about 16. So 14 million electron volts versus 16 million electron volts. And you can measure that energy by when the neutrons arrive at the sensor. So I just had inserted that slide again to remind you what this is all about. Next slide. So this is all about designing implosions. And the approach and the problems are all basically the same as the approaches and problems in designing nuclear weapons, at least the fusion parts of the nuclear weapons. You use the world's most powerful computers and immense computational physics codes to do that. I say they're the world's most powerful computers. Up until about 15 years ago, they were literally the world's most powerful computers. About 15 or 18 years ago, the people of Livermore started basically telling the computer chip makers how to make the chips in order to run them in a way that is matched to the kinds of calculations that are done. That's no longer the fastest calculation if you're just trying to store data, the largest computer if you're just trying to store data or something, but it's within the top 5 or 10 computers in the world, but it is the fastest computer for doing that particular kind of calculation. And I won't bore you with what that calculation entails, but it's another miracle. You're trying to control the instabilities in the implosion of that tiny capsule. Imagine a balloon, standard metaphor, imagine a balloon, you're trying to compress it, but if you've only got 10 fingers, the balloon, as you compress it, will pooch out around between your fingers. Well, that's an instability. And the reason the inside of the spheres have to be smooth to the size of a bacterium is so that those instabilities won't have a place to start from, or at least not a very big place to start from. You also have to, so fabricating the capsule is a challenge, but the physics challenges in the computations are to model the growth of the remaining imperfections, but also what I didn't tell you earlier is that you have to choose the materials and the densities of the materials in the shells because what is called a Rayleigh-Taylor instability happens where a material that is less dense is trying to accelerate a material that is more dense. A tiny instability in the interface between those two kinds of materials can grow. And it can grow to actually, the remnants of the instability can fill the whole inside of the capsule as it's imploding. But the densities and the pressures in those materials change as they are being imploded. So at 1 fraction of a trillionth of a second, the diamond shell may be more dense than the solid hydrogen shell inside it, but a fraction of a trillionth later, it'll be reversed. So you have to design the materials so that that reversal doesn't occur at the time that will lead to instabilities that will fall into the center of the burning fuel. So that's what these codes do. Next slide. So the team that did this experiment is about 800 people at Livermore, several hundred other people around the country, and about 100 technical people, both scientists and technicians and engineers from around the world. All coordinated by physicists. I have to put in a plug for Ernest Orlando Lawrence. It's really formally called the Lawrence Livermore National Laboratory because Ernest Lawrence was the physicist at the University of California at Berkeley that during the 1930s invented, I'll call it the management style, but it's really much more than just management. The style of using large teams of scientists and engineers and technicians effectively together to do big things like this. So it's using Lawrence's style, which is a clever, subtle way of letting every individual do his own thing while making it all work together toward an objective. That's the best I can do to explain it. Next slide. So how are we going to turn this into useful energy? So you might have to scale up the Livermore experiment. The Livermore experiment in December last year produced an amount of energy the equivalent to the amount of energy in 1 pound, about a pound of high explosive. A coal-fired or natural gas-fired gigawatt power plant makes about a ton of equivalent high explosive energy per second. So, I mean, that in itself is a mind-boggling idea. You've got to get enough coal into the burning chamber, and I don't know how a coal-fired plant works, but you've got to get about a ton of coal into it every second and keep the burning going in order to convert the heat produced by the chemical energy into electricity to make a gigawatt of power. So that's the goal for any kind of a power plant. So some approaches. The first thing and the only thing that might turn out to be easy or relatively easy is you've got to scale up the capsule to maybe 10 times, 20 times, 5 times the diameter of the capsule in the Livermore experiment. So that would be, if it's 10 times larger, that would be 1,000 times the volume. And if you can get the same efficiency of burn, you'd get 1,000 times the energy. And scaling upward ought to be easy, but the kinds of instabilities that can grow, well, the mismatches in what's called the acoustical impedance in the shells might not work at 10 times the size that it does in the tiny size. So you got to be very careful in how you scale up, but it's relatively easy. You've got to improve the power and efficiency of the lasers by at least a factor of 10. The lasers in the giant laser halls in the slide earlier at Livermore, that system was designed about 20 years ago. It took 20 years, it took 10 years to build it, and then 10 years to use it up until the last couple of years. So it's 20-year-old technology, laser technology. And if you were to start over again today, you could get easily a factor of 10 improved efficiency of the lasers. The ultimate objective, of course, is you use basically flash lamps to raise the energy of gas in the laser. You remember the little slide on the laser emission, laser amplification of stimulated emission of radiation. You use giant flash lamps to heat the material so that it will laze. Those lasers are about that big around. So that's basically the approach. And you would know how to do that maybe 10 times more efficiently if you were to do it today. Or you convert from a laser beam to a different source of energy. There is a vocal and smart minority of people who say that the right kind of energy to do this with is electron beams, not light beams. Turns out you can probably you can make an electron beam more efficient than you can a light beam, but it has its own problems because the electron beams themselves form their own magnetic fields. The electric current in the beam interacts with the magnetic field and can break up the beam. So there are problems with electron beams too, but there are also some advantages. So there are people working on that. The final challenge, which sounds as if it would be impossible to do, is to build a factory integral to the target chamber where the energy is being made that can make a capsule every second or 10 seconds, go through all those steps that took a month to do at the jewelry shop in Germany, go through all that every few seconds, place it in the center of whatever the source of the energy is, do that every few seconds. The people at Livermore have thought about this a good bit, and they've got the plans for a factory that will do what that bottom bullet says you need to do. It'll cost $10 billion to build the prototype of the factory, but that's nothing. Okay, the next slide. So today's fusion power enterprise, there are about 10 or maybe 20 large government-funded activities in the US, UK, Europe, Russia, and China that work on inertial confinement fusion, and about it's mainly the nuclear weapon labs in those countries that work on inertial confinement fusion, imploding the tiny capsules, because that's what you do in nuclear weapons, and people at weapons labs know how to do that. There are about 5 or 10 major magnetic confinement prototypes, of which the ITER, the donut approach in Europe, is a multinational team. The U.S. sort of, when I started Livermore 60 years ago, a guy named Ken Fowler was leading the world in magnetic confinement fusion experiments. Ken retired about 1970, and the people of Livermore did not follow up with a good magnetic confinement fusion program after Ken retired. But before he retired, he had developed a Ernest Lawrence type team around the country and eventually partly around the world that picked up the designs that started at Livermore in the 50s and 60s and carried them forward. And then that international team sort of shed Americans for 10 or 15 years. And now the international team is mainly not Americans, although there are some very good Americans. There's a good team at Princeton that works on magnetic fusion, but it's mainly overseas. There are, I learned in the Wall Street Journal about a month ago, 40 or so venture capital companies in both types of fusion power. Some started up 5 years ago, others started up 5 months ago, with lots of interesting off-standard approaches. Some of them look truly nutty to me, but who knows, maybe they'll work. So I think it's going to be about the 2040s at the earliest before you can get the first gigawatt fusion power plant. I thought about extending this talk to do my amateur assessment of how fusion stands with solar, wind, other renewables and so forth. But I thought I didn't know enough about that to do it, although I've got opinions. And fusion might be the really long-term source for energy for the world, but it is going to be long-term. So that's all I think I have to say this morning. Yes, right.
Ask your question, sir.
Yeah.
If you take a nuclear power plant that's running the rods and burning the rods, they're started in some type of fashion. I don't know how they start those. And they burn till they completely burn up. In this internal confinement system, where you blast them with magnetics or speed, that one little capsule is it. And how do you
Were
make
you talking about fission power? The current existing.
how do you keep the fusion going? I mean, you're talking about all this sophisticated concept to build this little tiny vessel
Yeah.
in Germany and drill tiny holes in
Yeah.
it and all that. And when that explodes, that's it.
That's it. He said,
How many of those you got?
Everything left? No, that.
You gotta keep making those
It was
things.
about a pound of high explosive. So it blew the capsule apart, and the target chamber, 10 or 15 feet in diameter, is heavy steel, and it's designed to contain a pound of high explosive.
So
But the whole round and the target capsule itself, it's all vaporized. I mean,
so it doesn't sustain itself?
no, it sustains itself for a trillionth of a second.
Okay. Where the nuclear rods, they just keep burning for
In
18
a
months.
fission reactor, the rods will keep burning for
18 months.
several years, or
Yeah.
however you manage the
It
reactivity.
doesn't seem practical. Who pays for all this stuff?
That's what the point. Go back a couple of slides. one more. That's the point of the last bullet on that slide, is an integral capsule factory that will produce, and so the target chamber would have to be able to hold a ton of energy, of explosive energy, rather than a pound. That's easy. The Russians have led the world in containing large nuclear explosions, 10,000 tons, in steel containment chambers. So that's a relatively easy thing to do, is contain a ton of explosion in a chamber.
So you've got two schools of thought. You've got magnetic confinement and internal confinement. Which one was Livermore? Which process?
Livermore, it was the inertial confinement.
Inertial.
Which is what happens in the sun, but with gravity rather than the inertia of the wall of the capsule.
Are you familiar with the Commonwealth fusion systems?
I'm sorry, say it again.
There's a new outfit called the Commonwealth Fusion Systems. Do you know which?
That may be one of the venture capital.
Do you know which process they're going to use?
I'm not sure.
Okay. Thank you.
Yes, sir.
With the capsules exploding, and that's what was bothering me. I know they're all using low melting materials, gold and uranium, and they're in a huger cavity. How is that directed? When the lasers go in and explode this thing, is it just go out?
The
Or?
energy largely comes out uniformly in every direction. A fusion power plant would have to put on the someplace, either outside or inside, because the neutrons will go through, that much steel. You can put it inside or outside, probably outside, so probably a plasticky sort of a material that absorbs the neutrons. So their energy is converted to the heat in that material that is around the outside and then you generate fluid through that hot material, just like you do in any kind of power plant, coal or whatever, to generate electricity. Yes, ma'am.
With nuclear power, you have spent rod, you have waste.
Yeah,
I'm not seeing where there's any waste with this
there's
fusion.
very little waste.
And is it radioactive in any
There
type
is
of way?
there is some radioactive waste. It's about 1% of the radioactive waste in a fission reactor. And it's much less dangerous because, and the way the waste is produced is the neutrons that have to be absorbed in some material outside the target chamber also activate that material a little bit, create some radioactive atoms, nuclei in that absorbing material. But it's about 1% and better, all of the radioactivity that's produced by the absorption of the neutrons in the surrounding materials is relatively short-lived. In fission, if you run the reactor the way most people run reactors, power reactors today, uranium fission has several steps, and one of them breeds plutonium, which is a more efficient fuel in a nuclear weapon. And so you have to protect it from some terrorists stealing it. Not easy for a terrorist because it's in heavy casks. But if you're worried about the safety of it, the half-life of the radioactivity in the plutonium is 26,000 years. So you've got to protect it for thousands of years. But the plutonium, the waste that lasts for thousands of years is because it lasts for a long time, its activity is not very great per second or per year. And so you do have to contain the plutonium for a long time, or run a reactor in a way that burns the plutonium too, so that there's no plutonium left. Which Jimmy Carter decided, and actually that was that was one of the 3 or 4 approaches to fission power that were put on the table in the 1950s, was to build reactors that breed their own plutonium from the initial uranium fuel, and then burn the plutonium. Because that fuel, after a couple of years, had considerable plutonium in it, even though it was still in the reactor, Jimmy Carter ruled out all of the approaches to fission power except the one we have yet today, which takes the depleted fuel out and stores the radioactive material rather than burning it inside the reactor.
Okay.
That may or may not have been a good decision, but it's what it did. Other
the materials of deuterium and the hydrogen molecules, how many of those do we have? You said it's unlimited?
If you there's deuterium everywhere. Cosmic rays make deuterium, so there's, I don't know, a burnable amount of deuterium in the room. Tritium requires another neutron, and the cosmic rays make it, but not in giant quantities. So you've got to basically distill the tritium out of much larger amounts of air in order to get the tritium out. But if you're going to make a deuterium-tritium reactor work, it's probably a small step to make a deuterium-deuterium burning reactor, not using the tritium, but having 2 deuterium nuclei fused. And since there's a lot of deuterium, that's probably the way, I should have said that on the slide, it's probably the way a fusion reactor would work. Other questions?
The capsules, gentleman was saying, it's mind-boggling to figure out how many capsules it's going to take. I have a manufacturing background. I'm just thinking what the process would be of having these capsules. I mean, like a machine gun or something, where there are several of them coming in at a time, or you need more lasers at a time, so you're burning more of them at a time, or it's got to be a
factory
crazy
is going to be pretty complicated. But I would say not any more complicated than the process for making one of those tiny fuel pellets. I should have brought a slide. Someplace I may have a slide of. Livermore hasn't thought about it. I should have said this whole activity of laser fusion, at least at Livermore and at Los Alamos, are part of the weapons program, the nuclear weapons program. Because just like I said, in 1960, the weapons people used stars to validate their design codes. Today they use this kind of experiment to validate their design codes. And since we haven't done any nuclear tests for the last 30 years, and the weapons age and corrode and so forth, and you've either got to live with the corrosion or replace the material that's corroded, and some of the materials can no longer be made by the process that they were originally made. And so you have to understand what the effects of all of those are on the performance of the nuclear weapons. And since the kind of process that occurs in a weapon involves these temperatures of hundreds of millions of degrees, you need a lab in the lab to be able to study the properties of materials at those temperatures and pressures and densities. And in order to validate your nuclear weapon reliability estimates. And so that's why the laser fusion program at Livermore and Los Alamos has been part of the weapons program. If this goes to more successes, my guess is that the Department of Energy, which does all this stuff, will establish a much larger inertial confinement fusion program for the purposes of producing inertial confinement fusion rather than providing experimental validation of weapon codes. Well, I thought you would appreciate the miracles there. I'm just mind boggled. What those guys have been able to do, guys and gals. The outgoing director of the Castle Design Program at Livermore is a woman. I forgot her name, but I used to know her and she was very smart. So, okay, thank you.